Hello. So, numbers. That's where we're starting. Is what is a number? What does it mean? What does it represent? Because the way the school teaches math, they just teach you how to manipulate numbers. They don't actually teach you what numbers mean. And so, number theory is actually a very important thing to know when it comes to understanding mathematics. And so, I'm going to start this off really quickly with just rational and irrational numbers. So you have rational and irrational. Okay. So rational numbers are, I don't like that. I might have to try to change that. Anyway, rational numbers are the ones that we work with. They're like integers. An integer is all your whole numbers, basically. Integers are basically your whole numbers. They're numbers that we work with, right? Because we have 9 main numbers with a 0 to represent 0. And so these are how we represent things in the universe. Again, I have 3 markers. And so these are the only things when it comes to real life mathematics. You're only working with these 10 numbers. And each of these numbers is a whole number, meaning that in our decimal system, our base 10 decimal system, the 3 has a 3 in the ones place with nothing behind it, right? So these are whole numbers because they are not broken up into anything. It is in the ones place, it's whole. What would be a non-whole number? It's going to try to put this into easy to understand terms. Would be like 3.2 or 3 2/3. Okay? These wouldn't be whole numbers because you now have an extra portion. If you think about it as like 1, 2, 3, 4, your whole number would be like right at this 3. You now have the shaded area. I don't know if that looks good or not. But the shaded area, you stop right here when you hit the 3. You know what I mean? It would be incomplete. It wouldn't be whole when you go between the whole number to the whole number. I think it's pretty easy to understand. So these are like every whole number has a stopping point. Okay, that's going to be very crucial. So y'all get it. Whole numbers. Okay, integers. I gotta clean my board. Stopping points. Stopping points are very important when it comes to rational numbers. Your physical world, the finite, is built on rational numbers that have stopping points. Okay? When you have 10 divided by 4, okay? 10 divided by 4. It doesn't go into it. You're going to have, 10 divided by 4, right? How many times does 4 go into 10? Twice. 8 minus gives you 2. Decimal, decimal. 0. Bring it down. How many times does 4 go into 20? 5 times. Boom. We hit a 0. As soon as you hit a 0, How many times does 4 go into 0? 0 times. Bring down a 0. How many times does 4 go into 0, 0? 0 times. You hit a 0. You hit a stopping point. That is the important thing to know about rational numbers, is that they will always come to a stop. So in your physical universe, think of building a house or like a skyrise. You have to have stopping points. Okay? Maybe I should have left that up there. You have to have stopping points to be able to build. Okay? You can't build something that never stops. Rational numbers. They're representations of the physical world, but this is also your finite. Okay. Rational numbers are finite. They end. Okay? That's important to understand, because in this universe, everything has a stopping point. The molecules in my hand know where to stop being skin molecules and start being air molecules. If they didn't have a stopping point, the molecules in my hand would expand out and mix with the air. The bones have to have a stopping point to get to the muscle. The muscle has to have a stopping point to get to the skin, the dermis. Okay? This marker needs to know how to stop and not go on for infinity. A flower grows and it needs to know when to stop. Okay? Everything in your finite universe has a stopping point. Okay. Irrational. Irrational is the code that your universe is built on. Okay, the code. Irrational numbers are pi, phi, e, square root of 2. Okay? These are your irrational numbers. These are so unique because these are the closest thing in our universe that represent infinity. Irrational numbers can't exist. They can't. But they do, which is what makes them so unique. But not only the fact that they can't exist, and yet they do, these are the code for the way that the physical universe works. So, when you're dealing, most people understand pi, right? Oh, 3.14 blah. Okay? Pi is the relationship. I don't like that sound. I gotta figure that out. So you've got, in a circle, so this is, the real world is full of circles. You can take any circle, you can get a measuring tape, and you can do this. You'll get close. The relationship between the diameter of the circle to its circumference is pi. Now, pi has every irrational number. It's irrational because it has no stopping point. Okay, no stopping point, ever. It goes on for infinity, and it's non-repeating, okay? A repeating number, it's always easy to do, would be like 2 over 3, right? 2 divided by 3. How many times does 3 go into 2? It doesn't. How many times does 3 go into 20? 6. 18 minus equals 2. How many times does 3 go into 20? 6. a repeating decimal. It goes on forever. We represent this by putting 6 with a line over it to show this is repeating. There are a ton of repeating decimals. And so this is just an easy one to understand. The only way that we know how to work with this is we have to give it a stopping point. We're going to say round to the nearest hundredth. And so the next digit, we're going to round this up. So this 0.6 repeating turns into 0.67. Because in order for us in the physical world to operate with things, we need to have stopping points. And so we will round repeating numbers to a certain degree, to whatever place value that we choose, because we can't work with infinity. So we have to choose a stopping point where we round that next 6 up to a 7. Okay? That's a repeating decimal that goes on forever. So you have repeating. Irrational numbers are non-repeating. There is no distinguishable pattern. And like I said, repeating numbers, you can do like, 40 over 9, I think it is 0.4 infinitely. You know, you run into, I forget what it is, 0.7, 0.27, 27, 27, 27, 27. You can get other fractions that have other repeating decimals, and they just repeat the same decimal pattern over and over and over again. This is just the easiest one to break down for people to understand. And so, irrational numbers have no stopping point, and they're non-repeating. There's no distinguishable pattern. And so, they represent infinity. But pi does shapes. Now, what y'all don't understand is that every shape can be broken down into a circle, because a square, right? Obviously, I'm not very good. I can see this. You just take a circle and you push out the corners to become a square. So it's like, I'm not going to get into that. Every shape can be represented as a circle. It can. But squares are easier to work with because they have stopping points. With a square, you can measure from here to here, and it comes to this and it stops. And it goes to this and it stops. Squares have stopping points, which is why the world and buildings and houses and everything is built on squares. It's because you can build on squares. Circles, on the other hand, you can take a tick tracer or whatever, and you can measure this circle, and you can just keep walking around it, and you'll never reach the end, because circles represent infinity. Because the perimeter of this thing, you can just keep walking around this and never hit an end, because squares represent the finite, circles represent the infinite. Okay? Pi. Infinite. Shapes, circles. Phi represents the way that things are built upon each other. 1.816 infinity. This knuckle of this finger times phi is this knuckle. This knuckle times phi is this knuckle. The length. This length times phi is this length. Okay? The way that your finger bends, that's phi. Your fingers, your geometry of your face, it's all based on phi. It's the way that nature, fractal patterns, pine cones, Fibonacci, phi. So phi is the irrational. It is the infinite version of Fibonacci. And I can prove that in another video. E is 2.71828 blah 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 infinity. It's the natural exponential function for how waveforms work. Square root of 2, you find that in Pythagorean theorem in triangles. And so the irrational, the infinite world writes the code for the finite to be based on. But you can't build on infinity because it goes on forever. You have to have stopping points for rational and finite. Okay? Which kind of comes through with like your evens and odds. Even numbers and odd numbers. Just real quick, I'm just going to do one more. So, finite, infinite. Even, and odd. Even numbers you can build on. Even numbers come to a good stopping point, and you can build on even numbers. Odd numbers, if you were to build a house with something larger than what's underneath it, it's going to fall. Okay? You need even numbers. They're going to represent your finite, and odd numbers are going to represent your order and chaos. And unless you're base 5, mod 5. But that's a video. That's the next video. Because 5 is the first odd number. 3s aren't as stable. 5s are very stable. That's why Roman numerals are based on 5, is because you can actually build on 5s. Because 2 odds make an even. This is 5. This is 10. Every time you double an odd number, it becomes even, so you can build on it. Okay. All right, I'm done. Finite, infinite, rational, irrational systems, and the idea of what numbers are and where they come from. And now that you guys have kind of a understanding that numbers, what they are and what they mean, that we can start working on rational stuff and we can start working on irrational stuff. Obviously the irrational is a bit more theoretical, but it governs the physical world. And the rational is more, how do we get into arithmetic to try and help y'all start learning how to calculate in your head. So